All right, welcome back. We are going to do section 6.8 today. This is essentially going to finish up our um, portion of the course on differential calculus. That is the calculus where we purely focus on derivatives and their applications. L'Hopital's rule is a rule that allows us to calculate limits of certain functions using their derivatives. So this is actually an application of derivatives. And let's start off with an example. We have so far learned how to calculate the limits of functions such as the following. We know how to calculate something like this. The limit as x approaches 1 of x squared minus 1 over x minus 1. If I tried to, say, directly plug in the value for x, then I would get the following. I would try 1 squared minus 1 over 1 minus 1, which is 1 squared is 1 minus 1 is 0 over 1 minus 1 is 0. So we have an issue here. I can't directly evaluate because I have division by 0, which is undefined. But I knew, this was back in chapter 1, how to kind of fix the problem. I can factor the function. I can say, well, x squared minus 1 is the same as x plus 1 times x minus 1. All that divided by x minus 1. And then we observe that we have a common factor in the top and the bottom that cancels. So this limit becomes the limit as x approaches 1 of x plus 1, which I do know how to directly evaluate. It is, it's 1 plus 1, which is 2. So we can say, because of that, that the limit as x approaches 1 of x squared minus 1 over x minus 1 is 2. So I evaluated the function, discovered that it is in this unfortunate form, which is called an indeterminate form. But I knew how to sort of fix the problem by algebraic techniques. What if I instead encountered this limit? Give you this as an example. The limit as x approaches 0 of e to the x minus 1 over x. If I try to directly plug in 0, I would get e to the 0 minus 1 over 0, which gives me e to the 0 is 1 minus 1 over 0. 1 minus 1 is 0 over 0. It's that same 0 over 0 form that we encountered before. However, if I look at this particular function for which I'm trying to find the limit as x approaches 0, it is not factorable. I could factor out a 1 out of the top, but that doesn't help me any. There is no way that I am aware of to fix the issue of the division by 0 as I was able to do in the previous problem. So there is no way to, I'm going to put quote, fix the problem, the division by 0 problem. Division by 0 problem by algebraic methods. By algebraic methods. So I'm going to rely on calculus here. We're going to bring in a rule by mathematician by the name of L'Hopital. and we're going to evaluate this limit. But first of all, I need to talk about something that I mentioned here. This is called an indeterminate form. There are multiple types of indeterminate forms. We'll talk about several in this section. Some of them are as follows. 0 over 0 is an indeterminate form. If we come to that, then I know that I cannot directly evaluate that limit. I have to use algebraic methods or other methods in order to find what the limit is. Infinity over infinity is another. Negative infinity over negative infinity is one. Or of course, infinity over negative infinity, or negative infinity over positive infinity. Those are also options. If I come to any of these forms, then I have to use a rule such as L'Hopital's rule in order to evaluate the limit. These are all called indeterminate forms. So let's talk about L'Hopital's rule. Let's suppose that we have two functions, f and g, and those two functions have the criteria that they are differentiable on an open interval, and that interval must contain the x value a, and it must, the second function g must be such that its derivative is not 0. If that is the case, then I have the following. If the limit as x approaches a of the function f of x and the limit as x approaches a of g of x both happen to be 0, and I'll just put as a note here, i.e. the limit as x approaches a of the ratio f of x over g of x has the form 0 over 0. If both limits are 0, then if I try direct evaluation, then I would get that form 0 over 0. If that occurs, then I have the following rule to evaluate that limit. The limit as x approaches a of that ratio, f of x over g of x, happens to be the same as the limit as x approaches a of the derivative of the top function, f prime of x, over the derivative of the bottom function, g prime of x. So I can find the derivatives of those individual parts of this ratio and evaluate the limit of the quotient, and perhaps that particular limit will be easier to evaluate than this limit. At least that is my hope with the application of this rule. So let's see how that works in practice. Okay, let's go back to that function that I referenced before. I want to find the limit as x approaches a of e to the x minus 1 over x. Okay, so it looks like I have a ratio of two functions. I'll call this top function f of x. We'll call this bottom function g of x. And we already noted the form. The form is 0 over 0, which is most certainly an indeterminate form. One of the ones that we mentioned. And it looks like from L'Hopital's rule that I need f prime and I need g prime. So let's find this. If f of x is equal to e to the x minus 1, then f prime of x is equal to the derivative of e to the x, which is e to the x minus 0, because that's the derivative of 1, which is just e to the x. And if g of x is x, then g prime of x is equal to 1. Okay, so I have the parts. Let's apply L'Hopital's rule. I know that the limit as x approaches, put a here, I should have put 0. The limit as x approaches 0 of e to the x minus 1 over x is the same by L'Hopital's rule as the limit as x approaches 0, that's same limit of f prime of x, which is e to the x, over g prime of x, which is 1. Okay? I know that these two are the exact same, or have the exact same value, I should say, due to L'Hopital's rule. Now, I'm going to simplify this. This is equal to the limit as x approaches 0 of e to the x over 1, which is e to the x. And now I can ask myself, can I apply the limit? This is equal to the limit as, is the limit as x approaches 0 of e to the x is equal to e to the 0 power, which happens to be 1. So yes, I most certainly can apply that limit. By L'Hopital's rule, the limit as x approaches 0 of e to the x minus 1 over x is equal to 1. Okay? I could not figure out that limit from this particular function, but because I applied that rule, I was able to calculate the limit. Now, let's talk through some steps as to what I did. Okay. All right. Oops. This is working well. There we go. Steps to using L'Hopital's rule. The first thing I want to do when I use L'Hopital's rule is I have to note the form. In order to apply this rule, it must be in the form 0 over 0, which is the form that was mentioned in the previous problem, or one of the infinity over infinity forms. That was not stated when I wrote down the rule for L'Hopital's rule, but it actually works the exact same way as the 0 over 0 form, but it does not work in a different indeterminate form, which we'll talk about in a bit. So I have to note that the form is in one of those indeterminate forms first and foremost. If I have determined that, then I can move on and say, well, okay, the limit as x approaches a of f of x over g of x can be determined by figuring out what are the derivatives of f and g. Okay. After I find them, then I'm going to calculate, well, what is the limit as x approaches a of f prime of x over g prime of x. I'm going to evaluate that limit if possible. Now, in that previous problem, we were able to find this limit after applying L'Hopital's rule. It will not always be possible, but we do have the option, if the limit is still in indeterminate form after we apply L'Hopital's rule once, to apply it again and again and again, as long as the function that we come up with is in one of those indeterminate forms, 0 over 0, or some form of infinity over some form of infinity, we can still apply L'Hopital's rule. Okay. One small thing to note here is, notice I'm evaluating f prime over g prime. I am not using the quotient rule to find those derivatives. I am differentiating the top and differentiating the bottom separately. So I am not finding the derivative d dx of f of x over g of x. I'm finding the derivative of the top and the derivative of the bottom as two separate functions. So I have to be careful about that. All right, enough of that. Let's move on and do another example. Okay. So I'm going to do this example. Let's figure out what is the limit as x approaches 1 of x cubed plus x squared minus 2x divided by x minus 1. Okay, first thing I want to figure out is what's the form? Can I directly evaluate? Let's plug in 1 for x. 1 cubed plus 1 squared minus 2 times 1 divided by 1 minus 1, which is equal to 1 cubed is 1 plus 1 squared is 1. So that gives me 2 minus 2 times 1 is 2 over 1 minus 1. So that gives me 0 over 0. This is most certainly an indeterminate form. Indeterminate form. Because I noted that, I can apply L'Hopital's rule. I can apply L'Hopital's rule, which I'm going to abbreviate as LH. Okay? Now, I've got to figure out what is my L function, or my F function, and what is my G function. Oh, whoops. A little eraser happy here. There we go. If I call this top function, F, and if I call that bottom function G, in order to apply L'Hopital's rule, first thing I want to do is find F prime and G prime. F prime is equal to derivative of x cubed, which is 3x squared, plus the derivative of x squared, which is 2x, minus 2 times the derivative of x, which is 1. I need G prime, which is equal to the derivative of x, which is 1, minus the derivative of 1, which is 0. Okay, so now I know that the limit as x approaches 1 of x cubed plus x squared minus 2x divided by x minus 1 is equal to, by L'Hopital's rule, here's where I'm applying L'Hopital's rule, it's equal to the limit as x approaches 1 of f prime, which happens to be 3x squared plus 2x minus 2, divided by G prime, which I know is 1. Oops, I should put that in blue, shouldn't I? That is 1. Okay, I can simplify that a little bit. That's equal to limit as x approaches 1 of 3x squared plus 2x minus 2. Okay, now I can most definitely directly apply the limit. I'll write it up here. Limit as x approaches 1 of 3x squared plus 2x minus 2. I'll plug in 1 for x. 3 times 1 squared plus 2 times 1 minus 2, which is equal to 3. So I could directly evaluate the limit once I applied L'Hopital's rule. All right, let's do another. Let's try this one. Let's try the limit. The limit as x approaches, let's say, 0 of 1 minus the cosine of 8x divided by 8x squared. Okay, let's figure out what's the form. 1 minus the cosine of 8 times 0 over 8 times 0 squared is equal to 1 minus cosine of 8 times 0 is the cosine of 0 over 0. Which is equal to 1 minus the cosine of 0 is 1 over 0, which is 0 over 0, which is an indeterminate form. Okay, so I can apply L'Hopital's rule. That is enough to tell me that I'm allowed to use that rule. So I need to know what are my f and g functions. This is my f of x function. And that bottom function, 8x squared, is my g of x function. Okay, so f prime, right, f prime is equal to the derivative of 1 minus cosine of 8x is the derivative of 1, which is 0, minus, I'm going to use chain rule here, derivative of cosine, which is negative sine of whatever's inside, 8x, times the derivative of 8x, which is 8, which is equal to 8 times the sine of 8x. And then g prime. G prime is the derivative of 8x squared, which is equal to 16x. And if that is the case, then this function, or this limit as x approaches 0 of 1 minus cosine 8x over 8x squared is the same by L'Hopital's rule as the limit as x approaches 0 of that top function, f prime of x, 8 times the sine of 8x divided by that bottom function, g prime, 16x. Okay, let's try to directly evaluate. Let's check the form. Sine, or 8 times the sine of 8 times 0 over 16 times 0 is equal to 8 times the sine of 0. Sine of 0 is 0 over 16 times 0 is 0. I still have 0 or over 0 form. This is still indeterminate. So guess what? I can apply L'Hopital's rule once more to this function. Write down the function again. Limit as x approaches 0 of 8 times the sine of 8x divided by 16x. We already noted the form. It is 0 over 0, which is indeterminate. Therefore, I'm going to once again, I'm going to call that top function f. I'm going to call that bottom function g. And I could call them anything I want. I'm just calling that top function and bottom function for this new limit that I'm trying to find. Which means in this case, f prime is equal to 8 times sine of 8x, which is by chain rule. It's the cosine of whatever's inside, 8x, times the derivative of 8x, which is 8, which I can simplify a little. That's equal to 8 times 8, which is 64, times the cosine of 8x. Okay, and I want to find g prime. G prime is equal to the derivative of 16x, which is 16 times 1, or just 16. Okay. And then this function, which I am trying to find the limit as x approaches 0 of, is the same as the limit by L'Hopital's rule as the limit as x approaches 0 of f prime, which in this case is 64 times the cosine of 8x divided by g prime, which happens to be 16 in this case. All right. Now I'm going to try again to directly evaluate. This is equal to 64 times the cosine of 8 times 0 over 16. Which is equal to, what is this equal to? Yes, that is correct. 64 times the cosine of 8 times 0, which is cosine of 0, which is 1, over 16. If I take 64 times 1 divided by 16, I get 4. So it turns out that that original limit, the limit, limit as x approaches 0 of 1 minus cosine of 8x over 16, over 8 x squared happens to be equal to 4 by applying L'Hopital's rule twice. Okay. Well, there are 2 examples of L'Hopital's rule. I believe that I will do one more example in another video.